When a patient comes into the hospital with stroke symptoms, the hospital will give that patient a CAT scan, which is a three-dimensional imaging of the patient's brain. The CAT scan needs to be examined by a radiologist, and the radiologist will decide whether to refer the patient to an interventionist, which is a surgeon who can perform an operation to lower the risk of long-term damage to the patient's brain function. After getting the CAT scan, the patient might wait for hours before a radiologist has a chance to look at the scan. In that period of time, the patient's brain function might be rapidly degrading. To speed up this workflow, a company called Viz.ai built a machine learning model that can recognize whether a patient is at risk of stroke consequences or not. Many people have predicted that radiologists will be automated by machine learning in the coming years. This episode presents a much more realistic perspective. First of all, we don't have nearly enough radiologists. So if we can create automated radiologists, that would be a very good thing. Second of all, even if this workflow has a cutting-edge machine learning radiologist in the loop, you still need the human radiologist in the loop. David Golan is the CTO at Viz.ai, and in today's show, he explains why he is working on a system for automated stroke identification and the engineering challenges in building that system. It's a great show about machine learning and healthcare. Before we get to the show, I want to announce that we're hiring. We are hiring writers and researchers and a videographer. And you can find these positions along with other jobs at softwareengineeringdaily.com/jobs. Some of these are part-time jobs, some are full-time. If you are hiring, you can also post your jobs on our job board. It's easy and it's free. Just go to softwareengineeringdaily.com/jobs and see how you can post a job. Over the last 2 years, I spent much of my time building a video product. We had issues with latency, unreliable video playback, codecs. I was amazed that it was so difficult to work with videos. As it turns out, video is complex, and figuring out how to optimize the delivery of video is not easy, especially since there is both mobile and desktop, and mobile users might not have as much bandwidth as desktop users. If you're an engineer working on a product that involves video, you just don't want to think about any of this. I can tell you that from firsthand experience. And that's why Mux exists. Check out mux.com and find out how Mux makes it easy to upload and play back video. Mux makes video hosting and streaming simple. And today you can get $50 in free credit by mentioning SE Daily in the sign-up process. Even if you aren't working on video right now, if you think you might work with video in the future, Mux is a really useful tool to be aware of. Check out mux.com, and if you're an engineer who's looking for work, you can also apply for a job at mux.com. On Software Engineering Daily, we've done 2 shows with Mux, and I know that Mux is solving some big, difficult problems involving lots of data and large video files. To find out more, you can go to mux.com. You can get $50 in free credit by mentioning SE Daily, and you can apply for a job if you're interested in working on some of these large challenges. Thanks to Mux for being a sponsor of Software Engineering Daily. David Golan, you are the CTO at Viz.ai. Thanks for coming on Software Engineering Daily.
Thanks for having me.
Your company identifies stroke victims, and it does that by looking at CT scans. What is a stroke?
So there are 2 types of stroke. There's hemorrhagic stroke and an ischemic stroke. Hemorrhagic stroke is when a blood vessel in the brain erupts. Essentially, the patient is bleeding into their brain. And an ischemic stroke is when a clot is dislodged from somewhere in the body. It can be from the heart or from the carotid. It goes upstream with the blood until it gets stuck in a vessel that's too small for the clot to. In both cases, the result is that there's a part of the brain that doesn't get the supply of blood and oxygen that it needs. As a result, begins dying quite rapidly. Ischemic strokes are more common. They make up to 90% of stroke patients. And that's the main focus of us at Viz.ai.
when a patient has a stroke, they're probably not at a hospital when the stroke happens. And so the response can be not great. How does the patient typically respond to a stroke?
So it really depends on the severity of the stroke. A stroke is quite an alarming experience. A severe stroke could manifest as one-sided weakness, loss of speech sometimes, some confusion, loss of words. Patients can lose consciousness, but it can also be, dizziness or headache or something relatively mild. In some cases, patients don't realize they're undergoing stroke. In some cases, their brain is sustaining so much damage that even though the damage is quite severe, they're not realizing it, and it's up to the people around them to spot it and call 911. Sometimes it happens during sleep, and of course, then you notice it only when you wake up. So yeah, it can take some time, but once spotted, people should get to the nearest hospital as soon as possible.
When they get into the hospital, the patient will get a CT scan. That's a scan that, it does an imaging of the brain. Explain what a CT scan does.
So CT scanner is like futuristic X-ray. X-ray takes you put the patient in front of essentially a camera that takes a picture of them, and the X-rays, they go through the body so you can see what's inside. But an X-ray provides you with a 2D image. So you can imagine you're sort of getting a flat image of what's inside of you. A CT scanner is a sophisticated version of that, where you take a series of X-rays and sort of get cuts through the body, and you can reconstruct those into a 3D image. So you get a full picture of what's going on inside. And specifically in the case of stroke, you get a full picture of what's going on inside the brain.
Is a CT scan a single image or is it a video?
So it's neither. It's a sequence of images, but they're not taken over time. So it's not like a video in the sense of a 2D image and the time axis. It's actually a series of 2D images that compose a 3D image of the body.
Okay, but it all represents the same timestamp?
Typically, yes. It depends on the technology. The advanced scanners today, they acquire most of the slices. Those images are called slices almost instantaneously. Older scanners would have taken longer and would have taken one by one or four after four. But nowadays, advanced tech the scans are done very, very fast in a few seconds.
Okay. So the CT scan gets created, and then in traditional medicine, the radiologist needs to look at the CT scan. And so there can be a long waiting time in that time frame because maybe the stroke happens in the middle of the night, person comes into the hospital at 3 a.m., and there's only one radiologist on staff. They're already too busy. They're looking at all these different patients, and this new stroke victim has to wait an extra hour or 2 hours or 5 hours to get a radiologist to look at what's going on. Why is that problematic?
Yeah, so when a patient is undergoing a stroke, the brain cells die at a very, very rapid pace. We're talking about the number is 2 million neurons die every minute. And that number doesn't really mean anything if you don't know how many neurons there are in the brain. But some other statistics are quite astounding. So one sentence that people like to use is save a minute, save a week. So every minute saved in time to treatment actually gives the patient another week of healthy life. People talk about 15 minutes translating into 4% increase in the probability of a lifelong disability. So it's really, really about those minutes and counting those minutes that can translate into very meaningful changes in patient outcomes. And then that patient walks into the hospital, and like you said, it can be in the middle of the night, and it can be a smaller hospital. It can be a very busy time where they come in at the exact same time that a car accident came in. And there's one ED doctor is trying to juggle all those patients, and there's one radiologist is trying to juggle all those patients. But actually, in the case of stroke, there's something considerably more dramatic. Starting in 2015, there's an approved treatment for stroke, for ischemic stroke, that's really making a huge difference for patients. And that treatment is mechanical thrombectomy, which is, from my perspective, nothing short of magic. So mechanical thrombectomy is the act of, through a small puncture in the groin, an interventionalist, who's a specially trained physician, can essentially take a wire and send it all the way to the patient's brain and retrieve the clot, essentially removing it from the patient's brain, thus renewing the flow of blood. And this treatment is so effective that in 2015, 5 clinical trials were stopped halfway through because the effect size was so huge that they determined it was immoral to deny the treatment from the control group.
Wow. Wow. That's incredible.
Yeah, that was a big moment in stroke care in 2015.
It's called mechanical thrombectomy. Is that what you
Yes.
said? So mechanical thrombectomy, this is a minimally invasive, well, maybe not minimally invasive, but it sounds like a fairly low risk. Is it low risk or
It's
medium
considered
risk?
fairly low risk. You talk to some doctors, they would say they would operate on a 96-year-old patient without thinking twice. There's always risk in this
Always
type
risk.
of thing. Relatively minimally invasive. People undergo interventions in the heart. Cardiologists do. Many people undergo them. They're considered fairly standard nowadays. So,
Always risk. So obviously, if you walk into a hospital and you get your CT scan, you don't want to just have a mechanical thrombectomy while you're waiting for the radiologist to come look at your stroke. You do want to at least have the radiologist look at your stroke or look at your CT scan and see how severe your symptoms are and whether you're having a stroke or whether it's something else along the differential diagnostic. But the point is that if you can get the stroke identified, the severity of the stroke identified, and it warrants a mechanical thrombectomy, the point is that we have a very high expected value treatment that we can apply to you as a patient.
Exactly. So there's really a golden opportunity for the stroke patient if they are identified on time and identified as a patient who's eligible for a mechanical thrombectomy. There's literally a magic wand that the interventionist can wave and remove that clot from their brain and generate huge benefits for the patient. Now, the biggest issue with this is, first of all, most hospitals don't have neurointerventionalist units, so they don't have the equipment and they don't have the personnel. Those are typically concentrated in the main hospitals, also known as hubs or comprehensive stroke centers. So you're in one hospital, you're being treated by the team there, but actually the person who needs to know about this case and really make the clinical decision is elsewhere, is in a different hospital altogether. And then, we've all been to hospitals, the doctors are doing their best, but sometimes there are inefficiencies in the system. So those doctors are trying to figure out what's going on with the patient and whether they're eligible for a thrombectomy. They would at some point try to contact the other hospital, consult with them, somehow transfer the images so they can also take a look on the other side. The interventionist then needs to decide whether they want to go in and try to retrieve the clot. And then the patient would be transferred to that hospital and operated on. So it's a very, very complex logistical effort where a lot of communication needs to go on and a lot of decisions need to be made by many, many people. And not all of these people are in the same place, and not all of these people are notified when this patient comes into the hospital.
And in the meantime, every minute is a week. So
Exactly.
if you can save any piece of time along this series of logistical time transactions, then this can be a potential boon. This can be the difference between very severely negative outcomes and severely positive outcomes. And if there's nothing wrong with the patient, or if it's something that is not a stroke and it's just maybe the patient's dehydrated or something like that, then if we can just get the patient out of the hospital as quickly as possible, that would be an added benefit as well. Not to bury the lead, this brings us to Viz.ai, what you're doing. So what you are targeting is when the CT scan gets created, instead of handing it off to a radiologist, which may take 3 or 4 hours, you just send it to the cloud and your software analyzes the CT scan. Explain what you can detect by running the CT scan through the algorithms that you've developed at Viz.ai.
Sure. So at Viz.ai, what we do is we get all the scans from the CT scanners to the cloud, like you said, and the scans are analyzed by our deep learning engine. And we're identifying those subset of patients that have an ischemic stroke of a subtype called a large vessel occlusion. So a large vessel meaning you can actually do a mechanical thrombectomy on them. So we identify those patients that can benefit from this magic treatment. And what we do is alert the interventionalists, the decision makers who really need to know about those specific patients and can help them and can provide them this life-saving treatment. We notify them on those cases. And they have an app, and the app rings very loudly to attract their attention. And they can view the scans and patient information on the app to verify our finding and act on it. And this is done within minutes of the scan, while typically they would be notified way, way, way later. And one thing that's really important to stress out is that we're not doing this instead of the radiologist reading the scan. Radiologists, they're not just looking at one thing. We're doing one thing, identifying those patients. They're looking at a bunch of other things. If, for example, there's evidence of cancer in the scan, the radiologist would pick that up. So we're not replacing them. The scan would still be read by the radiologist in the hospital, treated according to the standard of care. But we've identified that there's a subset of patients that could really benefit from expedited care. So if you look at that ER room that's packed with so many people, one of them can really benefit if we grab the attention of the right doctor at the right time. So that's our mission at Viz, getting the right doctor to the right patient at the right time out of all that crowd that's there in the hospital and get them the treatment that they need. We've been able to show really high accuracies and reduction in time.
In today's fast-paced world, you have to be able to build the skills that you need when you need them. With Pluralsight's learning platform, you can level up your skills in cutting-edge technology, like machine learning, cloud infrastructure, mobile development, DevOps, and blockchain. Find out where your skills stand with Pluralsight IQ, and then jump into expert-led courses organized into curated learning paths. Pluralsight is a personalized learning experience that helps you keep pace. So get ahead by visiting pluralsight.com/sedaily for a free 10-day trial. And if you're leading a team, discover how your organization can move faster with plans for enterprises. Pluralsight has helped thousands of organizations innovate, including Adobe, AT&T, VMware, and Tableau. Go to pluralsight.com/sedaily to get a free 10-day trial and dive into the platform. When you sign up, you also get 50% off of your first month. And if you want to commit, you can get $50 off an annual subscription. Get access to all three: the 10-day free trial, 50% off your first month, and $50 off a yearly subscription at pluralsight.com/sedaily. Thank you to Pluralsight for being a new sponsor of Software Engineering Daily. And to check it out while supporting Software Engineering Daily, go to pluralsight.com/sedaily. The workflow that we discussed before, where patient comes in, patient gets CT scan, waits for the radiologist to look at the CT scan. The difference between that workflow and the workflow we're describing with Viz is patient gets the CT scan, Viz processes the CT scan. If Viz notices something that is quite alarming, you can basically say, oh, okay, we need radiologist right now. There's something severely wrong, and we really need to alert you and get your attention. Is that right?
Yes. So just a minor comment is that we wouldn't alert the radiologist. We would actually alert the interventionalist, the specialist doctor who's going to perform.
So you would skip the radiologist in this scenario.
Yeah. So in that case, because for those specific cases, for those patients, at the end of the day, the interventionalist is going to look at the scans, look at the patient, and make a decision. So why wait? Why pass through first a radiologist, a neurologist, and then they need to get a doctor in the other hospital, call them, send them the images. Why let this chain of event go and lose time for the patient? Well, we can identify those specific patients that have a lot to benefit and send the information directly to the interventionalist's pocket.
Got it. Okay. So I think we understand at this point the value of this solution and how it improves the stroke triage system. So this sets us up to actually get into the engineering around this problem. So you need to be able to train an algorithm to look at three-dimensional brain scans and identify, is this a high-risk stroke victim or not? Where did you get the initial training data for this problem?
Data is always a hard problem, and especially in healthcare. Healthcare institutes are very protective about their data, for rightfully so. Patient health information is sensitive, and you want to protect patient privacy. Our original data sets came from academic collaborations, from researchers who bought into our vision, were excited about the opportunity just as we were, and could literally imagine a world where they get alerted and were living this problem day to day. So that's one venue. The other venue was partnerships outside of the US with radiology companies, hospitals, research organizations that were able to provide us with the right kind of data.
And how much data do you need to build an accurate model here?
So that's a good question. The amount of images that we ended up using is, I think, in the hundreds of thousands. I don't remember the exact number, but a lot of effort went into making deep learning work with a relatively modest amount of data. A lot of effort went into developing methods for data augmentation, for example, where you use existing data to artificially generate additional data points and making everything work. We've designed special deep learning architectures that were designed with the constraints in mind, and various ways. Deep learning is often viewed as this sort of black box where you throw in a lot of data and it provides wonderful solutions, which is quite often accurate. However, when you have not huge amounts of data, you sometimes need to help the network learn. So we develop various ways to sort of inject domain knowledge expertise into the learning process.
This data set, you needed to build a model to train the algorithm on that data set. Describe the training process. What was your sequence of steps to building this machine learning model and training it?
So, first of all, a CT scan is a big piece of data. It's actually, each slice is 512 by 512, and then you have a few hundred slices that you need to work with. So that's a lot of data. So, for example, one thing is that you don't throw all that into a network. One thing you do, for example, is focus on regions. We've, for example, identified the head. A CT scan can start from the chest and go all the way to the top of the head, and the brain is just a small part of that. So, for example, you can sort of crop out the head out of the scan. Then you sort of define the output that you want. That typically involves annotation on various levels. There's a high-level annotation saying, this scan is normal, this scan is abnormal, and there's lower-level annotation, so you can annotate things on the pixel level. So once you have all the data ready, you have your inputs, you have your outputs, and you start playing with your deep learning architectures, trying to get something that works.
How do you get those annotations done? Do you need specialists to label the data?
So we have a small operation of annotation, definitely. So some things require specialists. Some things can be done by more junior doctors, and some things can be done by a layman. So we have an annotation platform, and we have annotators of various degrees of expertise, and we leverage them for different tasks depending on the difficulty and level of expertise required for the task. So basically, for example, we define something that needs to be annotated. And just to give an example, so we'll have something to sort of run with. Say we want to identify, the brain. So we could have someone segment the brain on many, many slices. And that's not a very hard task. That's doable with minimal training by people with no specific medical training. So that would be an easy task that you can send out to minimally trained individuals. But if you want to identify, a small hemorrhage or a small abnormality in the brain, that really requires the eye of a specialist. So that task would go out to specialists who can log on to the platform when they have some time and annotate a few scans.
To be clear here, you had to build your own annotation platform, you couldn't outsource this to somebody like Scale API or some Crowdflower or something like that?
So we did start by playing with and trying to work with various existing platforms. They were lacking some features that were very, very specific to our context. So some examples are the fact that we need 3D data. So you need the ability to scroll through as if it were a video. Another thing is that CT data is not standard images. So for example, images are typically either 8-bit if they're grayscale, or you have 24 bits if you're RGB. CT scan, every pixel is a 12-bit grayscale. And the human eye can't really perceive a 12-bit scale. So what radiologists do is they apply a trick called windowing, where you essentially zoom in on a sub-range of this 12-bit scale and focus on the subtleties in that scan. And this is a dynamic process. As they read through the scan, they play with this window to identify, for example, the edges of a lesion, or where something starts and something stops. And this interactive nature, it just wasn't available in any existing platform. Another thing that was really important to us is to build in, for example, a hierarchy into the annotation tasks. So, for example, we were working with doctors from many parts of the world, and we wanted to have, for example, a unified lexicon. So our platform supports sort of a hierarchy where you can define a hierarchy of questions and tasks that they need to answer. So, for example, first question is the scan normal or not? If the answer is yes, well, maybe there's nothing more to do. But if the answer is no, then you can ask, well, what type of abnormality? And then the annotation task can depend on the type of abnormality. So you really, we've organized this in a very, very fixed manner. And then when different people annotate different things, they all use the same lexicon, and it's very easy to put all the data on the same frame of reference, so to speak. So yes, we've ended up building our own platform, which was a fun experience, I gotta tell you.
I want to take a step back here because this domain specific data labeling sector of the computer science economy seems to be something that is really developing. So I did a show with Scale API a while ago. And are you familiar with Scale? Do you know what that company does?
Actually, I'm not.
Okay. It's a pretty interesting company. It's kind of like upmarket Mechanical Turk sort of thing. So it's basically a Mechanical Turk API. So you can make an API call to get an audio file transcribed, or to get a picture labeled by a human that has been vetted. So it's like a very high quality API for Mechanical Turk style stuff. You might be able to make use of it somewhere in your pipeline, but they recently built a set of APIs around labeling self-driving car data. So, and they had to build an entire platform around this. So, you get a 3-dimensional image from a self-driving car, and there's not a good algorithm for noticing, at least, publicly available, maybe somewhere at Waymo, but for doing labeling of the setting within, can you label a pedestrian? Can you label, a strange circumstance in, maybe it's a road structure that is unique, like a roundabout or something like that, that's confusing. Because there's so many edge cases, they had to build their own platform for how people can manipulate an image, a 3-dimensional image, and create labelings within that image. It sounds very similar to what you're doing at Viz, where you had to build, it's not this straightforward thing of, we just had to bring in the humans and get them to label stuff. It's like we actually had to give them an interface for the labeling platform. Are there a lot of domains where this kind of custom data labeling platform is going to need to be built within whatever machine learning powered domain we're talking about?
So honestly, I think every company I know of in the medical imaging domain is supporting its own annotation platform.
Wow, that's bizarre.
Because everyone is a snowflake. Now here you need some semi-automatic tools, and here you need something specific for CT, and someone is doing there's a few really cool companies in doing pathology, and then you have 6 GB images, like huge images, very high resolution. And that's just not supported by standard platforms. So everybody is running into their own problems. And so far, back then when we started talking about this, we were interacting with a few companies about, doing things like you mentioned. But back then, we couldn't find any platform that was suitable for us. So we ended up writing our own. And now it's already integrated in all our data pipelines, and everything is working very well. So I don't know if we would jump off and switch to something else.
Of course.
But if I were to start a company now, there's a good chance that something better is available.
Yeah, interesting. You got this training process, you've got your data labeled, and then you need to put it through an algorithm to basically now since you have your labeled data set, and you have, I guess at some point, this data is getting labeled as stroke or not stroke, right? So you have the lower level pieces of data that you're labeling about the image, and then you have the yes or no case, right? The yes or no, we should escalate this to the interventionist versus not escalate it to the interventionist. Is that correct?
Yes.
Okay. So once you have those set of labels, what do you do? I mean, remind us, the process of, you have to train the data, you have to maintain some test data set. Give us an overview of this process as it applies to the stroke identification problem.
Okay, so you lucked out and you got big data set shared with you. Typically what we do, first step, like you said, is to divide this into train and test data. And test data is kept aside and keeping it away from the hands of the algorithms team, so they don't get the chance to peek into it. Now, just assume you've finished the process of annotation, you have your inputs and outputs, and you start training models. And you can start training models, or you can start working on pipeline. So a pipeline would be a sequence of steps versus a black box algorithm that's scan as input, label as output. We mix and match according to the context. So, one thing I mentioned earlier is this idea of, for example, cropping out the head out of the scan, which is very, very simple, but actually very powerful, because then you've reduced the amount of data needed to be processed by orders of magnitude. So basically you iterate on that, you investigate the successes and failures and try to figure out what you've done well and what you've done wrong, and how you can improve until you get to a point where you have something that's sort of working, and you're happy with the performance and you have a good feeling about it. At that point, you would go to your test set and get like a more objective quantification of your performance. And then once you've hit the target, which is a level of accuracy that we've decided that is reasonable for this product to be clinically useful, then you can go to the next step, which is getting this cleared by the FDA.
Right. Okay. So we'll get there in a second. Just to put a finer point on what you said, you've got these different parameters of the data set, or every piece of data in the data set has different parameters associated with it. And your process of iteration is going to be changing the weights of those parameters and being able to determine which of those parameters are most highly correlated with the stroke victims that should be sent off to an interventionist. And as you are modifying those weights, your model is getting better and better at identifying which are the parameters that matter. And you're going to be doing that on the training data for a long period of time until you have a set of weights on those parameters for the training data that works for the training data. And it seems to be like, okay, every time we put the training data through this algorithm, based on the weights that we've adapted for these parameters, we tend to get a really high accuracy of a really high precision of how the training set is being labeled as accurately or inaccurately. So now let's put it on the test data set. And if the test data set also is being accurately measured, that means that you have not overfitted your model to the training data. And that means that it's probably good enough to move on to the next step, which is actually like, putting this model into some bigger application. Do I understand it correctly?
That's exactly right. So you go through a process of training, which is, one part, like you mentioned, updating weights, using deep learning infrastructures like TensorFlow to optimize a deep learning model. So that's one part. The other part is more throwing in some domain expertise. So from simple things like here is a head to more complex things like, sometimes some people have metal in the brain, metal implants, and that's very, very disruptive to the CT scan. So we found out, for example, that removing those cases or including those cases really makes the life of the network hard because it's an event that's very rare, unexpected, and just metal on a CT scan is like this shiny white star. It's a very dramatic thing. So, for example, we came up with a simple heuristic that identifies those scans and sets them aside. So it's a combination of like knowledge-driven heuristics with really hardcore deep learning, which is like you described very well, iteratively improving those weights until you get the results accurate enough.
How do you fit in those outlier events to building a good model? Like when somebody has metal in their brain, how do you adapt to that?
So that's a terrific question, and it's a very interesting product question. So what does this mean? Can we have a product that doesn't work, for example, or when there's metal in the brain? And this specific example was an easy decision because metal in the brain often occurs when a person had an aneurysm and the aneurysm was clipped. So there's literally a metal clip inside that person's brain. And that's just so disruptive to the image that even experts often can't make sense of it. So in that case, we would not analyze that scan and we would alert the physician, notify them that there is a scan that we couldn't process. And another example is that if someone had a major surgery recently, and one thing that's common in the context of stroke is removal of a piece of the skull. So if a major piece of the skull was removed and there's a lot of deformation, and sometimes that can throw you off as well. And again, because this is actually a very special case, it's not sort of a case where you're expected to operate well. So maybe it's okay to say to the doctor, hey, there's this scan here. I'm not sure I know how to deal with it. Other examples are, less technical. For example, scans of children. So the brain of a child, the head of the child look very, very different. And at that point, we just didn't have a lot of that data in our data set. And we just felt uncomfortable that we would, we just said we can't run accurately. We're not comfortable with running this device, this algorithm on scans that we didn't have enough data from. So our labeling, this is like regulatory part, but the label of the device, it's a medical device, so it has a label and instructions, clearly states that it shouldn't be used on patients that are children. And if the metadata of the scan indicates that it's a person under the age of, I think 18, I'm not sure the exact age, we would refuse to analyze it.
Citus data can scale your Postgres database horizontally. For many of you, your Postgres database is the heart of your application. You chose Postgres because you trust it. After all, Postgres is battle-tested, trustworthy database software. But are you spending more and more time dealing with scalability issues? Citus distributes your data and your queries across multiple nodes. Are your queries getting slow? Citus can parallelize your SQL queries across multiple nodes, dramatically speeding them up and giving you much lower latency. Are you worried about hitting the limits of single-node Postgres and not being able to grow your app? Or having to spend your time on database infrastructure instead of creating new features for your application? Available as open source, as a database as a service, and as enterprise software, Citus makes it simple to shard Postgres. Go to citusdata.com/sedaily to learn more about how Citus transforms Postgres into a distributed database. That's citusdata.com/sedaily, citusdata.com/sedaily. Get back the time that you're spending on database operations. Companies like Algolia, ProsperWorks, and Cisco are all using Citus, so they no longer have to worry about scaling their database. Try it yourself at citusdata.com/sedaily. That's citusdata.com/sedaily. Thank you to Citus Data for being a sponsor of Software Engineering Daily. I think we have tackled the machine learning part well enough at this point, and I'd like to zoom out to the broader engineering setup at Viz. If I'm not mistaken, this is really the hardest engineering problem. What we just discussed is the hardest engineering problem in your organization. The other hard problems are things around FDA approval, some subjective decisions around, for example, should we skip people with metal in their brain, probably some other subjective product development questions. But as far as engineering, is there anything else that's particularly hard, like questions around the platform, the scheduling system for spinning up the machine learning infrastructure? What else is difficult in your engineering organization?
Okay, so first of all, I would like to say that I really don't think that the algorithm part is the hardest part.
Okay.
What I like to say is that we have the technology side. We're a stool resting on three legs. There's the algorithm, there's the infrastructure, and there's the app. And really, I don't think any one of them is harder or more important than the others. And specifically, so let me walk you through some of the difficulties here. So first of all, a CT scan is a lot of data. It can be several hundred megabytes to a few gigabytes. And you need to get it from the hospital to the cloud. And you need data infrastructure to move the data around in ways that are efficient, because every minute counts. So that's a major engineering challenge. Another thing is that literally when you count minutes and seconds, you need everything to run very, very smoothly. And on top of that, you need very high redundancy. So we're trying to design a system in the cloud that's very fast, very robust, that we can guarantee to our customers that it would work when they need it. That means, I think, high availability standards, cutting edge, and so on. Another aspect is cybersecurity. So because we're in the healthcare business, there's a big emphasis on cybersecurity, and everything needs to be done in a very, very secure manner, adapting to standard of care practices, very detailed and very elaborate architecture for a cloud environment, making sure that access is very well controlled and we comply with the various standards. So that's actually a very big challenge as a small startup with a small team operating under various standards such as the ISO 27K, cybersecurity efforts, HIPAA compliance, high trust. Europe now has GDPR. All that are things that you need to support with a small team of single digit number of engineers. So that's very hard. And the third part is the mobile app. And again, I think it's a very complex and interesting mobile app because we actually send all this data. We send the scan to the physician. And it's just a huge piece of data. It needs to get to them quickly. And there's anything from implementation decisions to be made to proprietary compression algorithms to get. And on top of that, what we really want, I'm sure you've been around hospitals, the IT infrastructure in hospitals is sometimes, I think, kind of old. And we see this as an actual opportunity to provide a novel platform to the doctors that's really delightful. And they all have smartphones, so they're used to a delightful experience. And then they walk into the hospital and they're working on a computer that's running Windows XP. So really want to provide them with tools to make their life easier. And that's another challenge. So it's an engineering / design / UX challenge. But it's also a very interesting challenge of how we make this an app that they would want to use for the other patients as well, because it's so much fun for them to use.
I have heard from people who have tried to build products for healthcare, and they just end up in this horrible situation where it's not anybody's particular fault. It's just the collision between Silicon Valley flavored product development and the process of getting something approved by the FDA, or just getting somebody within a healthcare organization to kind of like take a risk on you and your product. Those two things do not collide very well. Can you talk about how you managed to get people using this thing? Like, what was the process of, for anybody out there that's listening that is trying to get a product approved by a hospital or to get a product trialed by a hospital or a medical organization, what advice do you have?
Okay, so that's a really, really good question. And I think healthcare does present some complexities. At least in that case, maybe some lessons from general B2B can be transferred. But generally, you want to do something. You want a solution that helps three people in the organization. The patient, obviously, the doctor, because that doctor is going to be your champion. B2B sales, you always identify the champion that's going to push your product through the system. And then you have the administrator of the hospital or the CFO or someone who gets these requests from many, many doctors within the organization, and they need to make a decision on the budget. So they need to understand or see something in it for them in the bottom line or in the top line or both. So for us at Viz.ai, I think the case for stroke is very, very appealing. First of all, for the patient. I think that's obvious from all we discussed. Every minute counts. Getting there faster, that's wonderful for the patients. The doctors, at least our feeling was that they've bought in quickly. This is, more than once I had a conversation with an interventionist in a conference and said, this is what I need. This is what I want. This would make my life much, much better. So, if you don't have that kind of support, you would have a hard time if you don't have a champion. The last part, I think, is the hardest because often, and I know many stories, I have friends in companies like you mentioned who've built great products that could save lives or improve, patients stay in the hospital or reduce, time, do all sorts of good things for the patients, but there's no strong financial incentive for using them. And that's really the tricky part. So the case for stroke is very appealing financially also. First of all, stroke is, in the top 5 killers in the Western world. I think in the US is number 4 or 5, but it's the number 1 in healthcare spend. And that's because when someone is having a stroke and is not treated, they can remain handicapped for the rest of their lives. They would need assisted living. They're losing income. Their family is losing income. The insurance is paying for that. That's just a lot of money. So, there's just big incentives there. That's actually very important that the system would have something to benefit financially from using the device.
From a product development point of view, what I heard you say there that stood out to me was there's this moment that you can set up for at a conference, for example, where you're at a conference, maybe you have a booth set up and you can demo to doctors, here is what you do to use our software. Here is how it saves you time. Any questions?
Yes.
Right? Like you need that demo moment. You need the wow moment where somebody can say, this is so concrete to me. This is not like, you've given me, here's a new CRM platform for your patients, right? Where it's like, here's a tool you can use to change your entire workflow within the hospital. That is not how you convince somebody to start using your software in healthcare.
No, not at all. Not at all. You need to get that aha moment where you talk to them about their institution, you talk to them about the hospitals that they're getting patient referrals from. You ask them, how long does it take? Do you have any issues? Do they always call you within the 30 minutes that you're required to by the guidelines? And then they say no. And then it's like, well, how would you feel if you get an alert on every positive case? And that's that wow moment where they typically realize there's a very interesting value prop here for them and for the patients. Another thing, if you're talking to administrators, and that's actually another big thing in stroke, is guidelines. So because stroke is such a big burden on the healthcare system financially, hospitals are required to abide by certain guidelines on how fast they treat those patients. And this goes back to the offering for the administrators of the hospital, because what we're offering them is we can help you improve your statistics and retain your status as a high-performing stroke center. So that's also very appealing.
We also had a show with a company called HeartFlow. You're familiar with HeartFlow?
Yes, yeah, they're awesome.
Okay, yeah. So it sounds remarkably similar to what you do in the sense that they look at CT scans of hearts and they make decisions around who should get a stent in their heart or not. How does that problem domain compare to the stroke identification problem set?
So I'm familiar with them, with their product. I don't know their technology very intimately. I think these are slightly different problems. So with HeartFlow, to the best of my understanding, and again, I apologize if I'm misrepresenting, you're essentially acquiring a dynamic scan where dynamic scan is acquired over time. So we would essentially scan the heart again and again and again while injecting contrast. So the contrast, shows up on the scan, and you can see the veins and the arteries, and you can see the progression, and you can use that to sort of make a 4D model, a hydrodynamic model of the vessels around the heart, and address those important clinical questions that HeartFlow are addressing. So, for example, are the pressures, what are they? Do they justify a stent or not, and all that. So that's very, very interesting. In our case, their decision it's not about time, it's about they're there and they need to make a clinical decision, but they want to diagnose the patient accurately and treat them. Our case, the focus is on, it's essentially a yes-no question. Should we take this person for a mechanical thrombectomy or not? And that question needs to be answered as fast as possible. So that's actually something that really separates, I think, Viz.ai from many other companies in the medical imaging domain. Everybody are doing amazing things, really. I think there's so many interesting and great companies, but we're operating at a very, very high pace, right? We need to give the answer now. There's no waiting. Right now, for example, a woman does a mammography scan, she gets an answer within 2 or 3 weeks, and that's fine, right? And if a startup is working on better breast cancer detection, that's really a wonderful cause that's going to save many, many women. But there's no time factor there. So it's perfectly fine for your engineering organization to be, for example, skewed towards a very strong algorithms team and some engineering wrapping around it that handles, moving the data around. In our case, that's why I said we have those 3 legs that we stand on. It's getting everything to work, and getting everything to work fast is just as important as getting the answer right. So that sort of differentiates us from many of the other players.
Understood. And I know we're up against time here, so I want to ask you, kind of in the same vein of the previous question around HeartFlow, this abstract market of, we have a problem within the healthcare world that we can solve with machine learning, and none of the individual problems within this, whatever problem set we're talking about is particularly hard. We just need the data. We need somebody to build the machine learning model. We need somebody to build the back end, and we need somebody to write the mobile apps, and we need somebody to do the sale at the conference. So we need these different things. None of them are that risky. We just need the right team. We need the right sequencing. We need the right project management. How many of these opportunities are there in healthcare? Is this something where people could just get involved in healthcare, spend 5 months, find a problem, and build a product?
I think that's maybe slightly
making it
exaggerated.
Okay, exaggerate.
I think it's some of the issues is if you define a problem and you say, I'm going after this, do all the process you mentioned, but get the data, build the algorithm, build the infrastructure, build the app, you will get there. Honestly, I think one of the biggest challenges is generating this value offering for the hospitals, for the patients, doctors, and administrators. That's very, very tricky, and you would need to iterate quite a bit on that. There are opportunities. I think we're seeing a wave of companies emerging with interesting value props for healthcare. But I think we've also seen some companies who tried great talent and backed up by VCs and with funding and all that, and they didn't crack it because it's not just about building a technology that works. It's building a product that works and is used and is loved and effective. And the best algorithm in the world is useless if it's not part of one Lego brick in a product that's delivering value across the entire chain.
Understood. David, I'm sure we could talk for a lot longer, and if you got another product in the future or some further announcement, as I'm sure you will have eventually, I'd love to have another conversation, something, there's so much stuff that I didn't get to, but I really want to thank you for coming on Software Engineering Daily. It's been great talking to you, and I'm inspired by what you're working on.
Thank you very much. I really appreciate the opportunity to be with you and speak.
At Software Engineering Daily, we have a web app, we have an iOS app, an Android app, and a backend that serves all of these front ends. Our code has a lot of surface area, and we need visibility into problems that occur across all of these different surfaces. When a user's mobile app crashes while playing a podcast or reading an article, Airbrake alerts us in real time and gives us the diagnostics that let us identify and fix the problem in minutes instead of hours. Check out airbrake.io/sedaily to start monitoring your apps free for 30 days. Setup takes only a few minutes, there's no complicated configuration needed, and Airbrake integrates with all of your communication tools from Slack to GitHub to Jira, and it enhances your current workflow rather than disrupting it. You can try out Airbrake today at airbrake.io/sedaily. If you want to monitor and get visibility into the problems that may be occurring across your application, check out Airbrake at airbrake.io/sedaily. Thank you to Airbrake.
Wow.